Thank you for the reminder.
Okay, it's great to be here. Thanks for the invitation to come and talk to you guys about some of the work that I and other people have been thinking about in terms of how we're currently looking at exoplanet atmospheres and then what we might want to do in the coming years as we get more capabilities. So in the field of exoplanets, we're of course pushing down to be able to observe planets that are like this lovely planet that we know and love today. We're not there yet. We're observing many other interesting things along the way. And I wanted to start this talk actually back in the year 2000, before we knew of any transiting planets until the very first one was discovered. So this, in many ways, is what really kicked off the field of exoplanets as I know it, where we have planets that we can start to think about characterizing their atmospheres. This is Charbonneau et al., 2000, and measured this. This was a hot Jupiter-sized planet in a short orbit around its star. And this really put the nail in the coffin for any of people's theories about how maybe these signals that we were seeing were not planets. It was very clear that this had the mass and the radius of an extrasolar Jupiter-like planet, just in a much different orbit than anything in our solar system. In the same year, we had this discovery, which was enabled by the advent of infrared surveys across the whole sky for the first time. So really mapping out what the sky looks like in the infrared. So this paper published by Gizes et al. Took the 2-mass data as it was being published. This paper is full of a lot of interesting things. One of the things that doesn't look interesting is this table, but amongst this table is this particular object, which is a very late type M dwarf. And we'll come back to why this might be a specifically interesting target later on. Okay, in the meantime, our knowledge of the kind of demographics of exoplanets has just totally revolutionized in the past decade. This past decade that we've just lived through is really where we learned where planets are in systems near to us. So this is looking at the known planets as of 2009 in planet radius versus the orbital period. So you could see that we had this cluster of transiting large planets around the size of Jupiter, just a couple of these smaller planets, and then the blue ones here are planets that are not transiting but were found with the radial velocity method. So that was the demographics until we had this lovely little spacecraft that observed a patch of sky just to find transiting planets to unprecedented sensitivity. So of course the Kepler telescope. And Kepler did this to our understanding of exoplanets. So Kepler really pushed to find not just the easiest things to find, these hot Jupiters, but really was sensitive down to planets of about the radius of the Earth, and we really filled in this space with planets that we never even predicted would be there, with radii between the size of Neptune and that of the Earth itself, where of course we have no examples of planets like that in our own solar system. Okay, so that brings us to 2016, where we looked with the Spitzer Space Telescope at that star from the first slide of my talk. This star, this M7.5, really late type M dwarf. People observed it with Spitzer for days, right? Like if you look at this is in Julian days along here. So it's this long observation with Spitzer, and found in fact that this small, interesting nearby star has in fact all of these dips in the light curve, that each of these is a planet in the system, color-coded here. So you can see that once you stack all of this data together, you find that there's these 7 planets, and this is the TRAPPIST-1 system. So planets B through H in increasing distance from their host star. So this is really one of the most incredible discoveries in exoplanet science in recent years.
This was not who discovered. They had some inside information.
That is true. So they had a whole survey to be looking at stars to do this. But the Spitzer light curve is just exquisite. Okay. So in early 17, we found these 7 planets orbiting the small nearby star. And once you figured out kind of what their temperatures were likely to be, some of these in the middle, kind of in the E and F range, could be amenable to having liquid water on their surface, of course, depending on what their atmospheres are actually made of. And so for the first time in human history, we have a sample of temperate Earth-sized planet for which I'm going to argue over the course of this talk, and we'll get there at the end, that I think we might be able to detect the atmospheres of some of these planets. Okay. So we now have this census of planets. This is now showing known confirmed planets here in period versus the mass of these planets. And they cover, we've gone from having these larger, hotter planets to kind of gradually finding these cooler, smaller planets. And so the field of exoplanet discovery has always been pushing in this direction. And what I'm going to talk to you about today is how indeed in the field of exoplanet characterization, we're doing something very similar right now, just a few years behind what people are doing in exoplanet discovery, to go from characterizing the easiest targets up here to the hardest targets along here. So we're poised to take the same path here, and I'm going to go through this over the course of my talk. And of course, along the way, right, we're trying to get to this point where we can start characterizing Earth-like planets that could bear life. But the path along the way is filled with all kinds of interesting planetary astrophysics that really sets up the stage for being able to understand what we find when we get to this point. And so some of the things we might want to learn about exoplanets. So I'll throw a couple things out here that are the kinds of measurements we want to make to really understand something about planetary astrophysics. So this is one of those things. So when planets form, they end up with different compositions in their atmospheres. So this is what happens in our solar system. So in our solar system, if you look at the mass of the planet versus the amount of metal it was able to accrete into its atmosphere, you see that there's a strong dependence here, where more massive planets have low metallicity atmospheres, something like 3 times solar composition. This is all based on the methane abundance in the atmosphere versus the hydrogen. Saturn is enhanced by about a factor of 10, and then Uranus and Neptune are in fact enhanced by a factor of about 100. And so in the solar system, what we think is happening here is as we go to these small planets, we're accreting more solids into our object than the gas in the protosolar nebula. And so for exoplanets, we of course want to figure out if this is a universal property, or maybe we have some small planets that actually just accreted some gas onto them and don't have a lot of ices that formed. Maybe if they were closer into their host star, they formed in a very different way and would have a totally different pattern of abundances here. And so we want to really map out what else the metal enhancement and the composition in general of our atmosphere depends on for these planetary systems. And of course, we're not just accreting all metals all together, we're accreting different amounts of materials differently. So this is showing what we might expect as a distance from the host star and how much of the material is in grains versus gas depending on what has condensed out, so what temperatures we've gotten. So each of these is what people call an ice line, where you condense out water ice here, CO2 ice here, and CO. And so depending on how much of this gas versus how much of this grain material you accrete, you might expect to have a different carbon to oxygen ratio in your atmosphere. So this is also something we want to map out and see if this theory of ice lines actually seems to hold, or if there's something different going on. And then another thing that's currently totally a mystery is what exactly these objects that are in between the size of Earth and Neptune are like. So as I said earlier, we don't have any examples of planets like this in our own solar system. This is what we see from just the demographics here. So in the demographics, we see that there's a lot of Earth-sized planets. There's this dip that was recently discovered just a year or so ago. And then there's this increase again in these kind of sub-Neptune-sized planets, around half the size of actual Neptune. And then it falls off after that in how many planets there are around these stars. And so we really don't know which of these in the middle are scaled up versions of something like the Earth, which are scaled down versions of something like Neptune. And so we really want to look in detail at these planetary atmospheres to figure out what they're actually like. So we observe transiting planets, which is most of what I'll talk about today, in a couple different ways. So I'll talk through this briefly here so you understand the actual measurements we're making to be able to see these planetary atmospheres. So one of the ways is with transmission spectroscopy, which exploits when the planet goes in front of the star. And the other is thermal emission spectroscopy, when the planet passes behind the star. So in transmission spectroscopy, the idea is that the opacity in your atmosphere is dependent on the wavelength you're looking at, because you have different molecules that absorb at different wavelengths in your atmosphere. And so you're measuring the transit depth, and in fact, the planet actually appears to be slightly smaller at wavelengths between major absorption features and slightly larger where your atmosphere is able to absorb very efficiently. So you'll see a change in your transit depth that indicates a change in your planet size as a function of wavelength. In thermal emission spectroscopy, so now instead of in this geometry where we're looking at the transit here, we're now in this geometry where we're looking at this very small eclipse when the planet is eclipsed by its host star. And so the planet will be glowing at different temperatures depending on what's absorbing in its atmosphere. And so the idea here is we measure the depth of that eclipse. We plot that as a function of wavelength. So we do that for many different wavelengths. And then we do what I do, which is fit models to these data points to try and understand what the properties of this planet actually are. Okay, so this spectrum is obviously not a real spectrum, so I'll show you a couple real spectra now, starting with the easiest things, so kind of what the cutting edge right now is for the easiest targets, the hot Jupiters. And so this is really the state of the art. So this is emission spectroscopy and transmission spectroscopy of this kind of normal-ish hot Jupiter planet, WASP-43b. So this is a hot Jupiter that orbits a K-dwarf. You can see it's about the size of Jupiter, about twice the mass of Jupiter. And they used for these observations what has become the workhorse for doing this kind of work for transiting planets, which is wide field camera 3 on HST, using the grism that goes from 1.1 to 1.7 microns, which is ideal because it covers over this molecular feature that we're trying to detect from water. And so they observed 6 transits and 5 eclipses to get to a really high precision measurement, less than 50 parts per million per wavelength channel that you see here. So then we go from these eclipse depths and transit depths as a function of wavelength and can plot them as spectra here. So indeed, this is the emission, this is transmission. You detect the planet increases in size where you have this water feature that's causing more opacity in your atmosphere. So that's detected at high significance. And then here, this is an emission. You see an absorption feature where the water is absorbing at 1.4 microns here. So then you can spend a whole PhD figuring out how to go from these two things to having a posterior distribution of the water abundances that could be in the atmosphere that would allow you to match both of these spectra at the same time. So that's what you're seeing here. And so this really has been the first measurement of the water abundance to relatively high precision compared to what had been done before in an exoplanet. So you can see that it's consistent with a solar metallicity atmosphere here. Okay, so that's the state of the art for what we can do for hot Jupiters. We can now do this for kind of a handful of the hot Jupiters we've been able to observe so far. But of course, one of the things we want to do is push towards these interesting planets that are between Earth and Neptune in size. So I'm going to talk a little bit today about what we've learned about one of my favorite of these objects. So this is the kind of canonical sub-Neptune planet, GJ1214b. You can see it falls nicely in this region between Earth and Neptune in size. It's about 6 Earth masses, 2.7 Earth radii, and it orbits a really small star. And this turns out to be super important because we need, for these really high precision measurements, we need a high planet size relative to the stellar size. So this helps a lot. And so people went out and did the same kinds of observations that they had done for, WASP-43 to get these really high precision measurements to really high fidelity to be able to detect water in GJ1214b. And this is what they found. So they measured the most exquisite flat line that has ever been measured in exoplanet science. This remains the most exquisite flat line. So you can see here, indeed, we see no features across this 1.1 to 1.7 micron wavelength region. And in fact, these lines here represent models of different high-density atmospheres. So a totally methane, 100% methane atmosphere, 100% water atmosphere, and 100% CO2 atmosphere. And we can rule out all of these, even very high-density atmospheres with very small scale heights, to high precision. And so this was really interesting, and people sat around and thought about what this means. But what seems to be happening here is that GJ1214b has aerosols that are in its atmosphere, as well as these molecular gases that we're trying to detect. So there's some kind of clouds or haze particles that are high up in the atmosphere that are obscuring what spectral features we think should be there from 1.1 to 1.7 microns. Yeah?
I have what I think is a very stupid question, but in the previous slide, is this the reason that maybe the artist presented it as brown? Do we think, is this the kind of evidence that would make us think that this planet is in fact brown?
Yeah, so, yeah, that's interesting, because this planet was first billed as a water world, because if you plot its density, it has the density of if you had 100% water ice planet. It has the same density as GJ1214b. And so over the course of these results as they were coming out, we realized that that it was definitely not that, but instead surrounded in what we think could be a photochemical haze, so something like soot in the atmosphere. So yeah, it's, yeah.
It actually might look brown.
It might look brown.
That's kind of cool.
Yeah. Okay. So now I'm going to tell you a little bit about the kinds of photochemical hazes that we think could be forming in this kind of atmosphere that could match these observations. So hazes form generally in atmospheres that are irradiated by UV flux, like most of the atmospheres in our own solar system have some kind of haze particulates in them. My favorite is Titan. So Titan has this thick hydrocarbon haze layer that obscured what we could see until we actually flew a spaceship there. So we want to not have to do that for exoplanets. So the idea here is that you take an atmosphere that's rich in methane, you add UV light, and then it starts this whole chain of methane photolysis and subsequent chemistry that gives you what I've been calling these soot precursors. So things like acetylene and ethane, HCN in the atmosphere. And we can model how this happens. So we can use a photochemical model. This is of GJ1214b, a model of it. This is showing the amount of different species versus pressure, which is a proxy for height in the atmosphere. So you can see, indeed, as promised, right at the top of the atmosphere, your methane decreases sharply up here where you have the UV photolysis happening, and you start to form all of these soot precursor kinds of materials. Okay, and then we think that the conditions are right in these atmospheres to continue this chain of chemistry to make longer chain hydrocarbons, things like polymers that stick together that can actually condense in a 600 Kelvin atmosphere, right? Because GJ1214 is a warm-ish sub-Neptune. It's about 600 Kelvin. Materials like acetylene are really volatile. They're not going to condense into solid particles in the atmosphere. So we need a larger particle that's actually going to be solid, like a soot. And this turns out to be basically impossible to model this whole chain to long chain hydrocarbons from first principles. You can't do it with the photochemical model. We don't understand the kinetics well enough for all of those different reactions that can happen. And so where we don't have theoretical simulations, we can actually do this in the lab. So this is one of, I think, the coolest results to come out in the last couple years in our study of hazes and clouds in exoplanets is these results from Sarah Hurst's group at Johns Hopkins, who's actually set up like a test tube, basically, with all of the ingredients that we think are in these atmospheres, and then they hit it either with a plasma source or with UV light to see how much of these hazes start forming, what they're likely forming from, what the kind of processes are that are happening in these atmospheres. So I don't have time to go into the details of everything they found, which is all super interesting. But what I'll show is that for atmospheres that are somewhat enhanced in metals, so something that we might expect for a planet that's a little bit more enhanced in metals than Neptune, which is 100 times solar metallicity. So for 1,000 times solar metallicity, for temperatures that are 300 to 400 Kelvin, we actually are producing more haze particles here than in the standard Titan atmosphere, which is, of course, this really hazy world in our own solar system. So I think the experiments are really saying that in these atmospheres, we really might have exactly the right conditions to form these hazes.
Just want to assume that if you went to 10 or 1, let's see, there's nothing. It's dropping off in the form of that peak.
I think it would, yeah, because if you look at the chemistry of the underlying gases at 100 times solar metallicity, it's really not that different from 1 or 10 times solar metallicity. So what's going to happen is you'll just scale down the amount of metals that you have in the atmosphere. Yeah. But we still think some of those objects could be hazy, so.
What is the temperature of Titan? How would it compare?
The temperature of Titan is 92 Kelvin. Yeah.
So it must have made it sense much earlier? Or since it's so cold, it's easy to keep them there?
Yeah, so more things will condense in Titan's atmosphere, so you don't have to get much bigger than these. You can't quite condense these, but you can stick a few of them together into something slightly bigger and condense that. So then it's all a question of how fast those interactions happen at the really cold temperatures in Titan's atmosphere. So again, people can't model that from first principles. They do it in a lab. That's why this work was all pioneered for Titan in the lab. Yeah. Okay, so then we can include some of these soots in our atmospheres, the predictions that I ran for GJ1214, and we see indeed that hazes, if we include them in the atmosphere with some parameters that I won't talk about here, we can indeed match this really flat transmission spectrum. We can get enough material to be able to match it. So that's good, right? We can do that for one planet. But we haven't really nailed down that it has to be these photochemical hazes. It could be something else that's flattening the spectrum. But the advantage of doing exoplanet science versus doing planetary science in our own solar system, where we only have one example of each planet, is that we can look at many planets. And so what do we expect to see if photochemical hazes are really flattening the spectrum? What do we expect to see as a function of temperature? So here I'm showing, compared to GJ1214's incident flux, which gives it a temperature around 600 Kelvin, scaling that, what do we expect to find for the amount of soot precursors? This is showing the amount of soot precursors above some height in the atmosphere. We need them up high to flatten the spectrum. And what we see here is that we have this really sharp temperature dependence where we increase in the amount of these soot precursors right in the middle here, and then decrease dramatically at about 1,000 Kelvin or so. And that's because we transition from having a methane-rich atmosphere at low temperatures to a carbon monoxide-rich atmosphere at high temperatures. Carbon monoxide has this really strong bond. You can't really break it very easily with UV light. And so we don't start the whole chain of methane photolysis from breaking up this methane. We just never start that with CO. And so we never get any of these, or a very limited amount of these soot precursors forming. And so now it turns out we have just enough sub-Neptune and Neptune-sized planets to start looking at whether this is actually true for the planets that we've observed so far. And just enough in terms of exoplanets is 6. We have 6 planets. That's good enough for statistics, right? So they're stacked here. These are all observations from Wide Field Camera 3 on HST, and they're stacked from the hottest object here to the coldest object, which is our flat line here, GJ1214b. It's really flat. Yeah, I told you, it's exquisite. So you can see that not all of them are flat. Some of them are flat to within the error bars, but in, say, HAP-P26, which is a Neptune-sized planet, and HAP-P11, which is also a Neptune-sized planet, we can see this nice modulation that we predicted would be there from this water feature. So that's good. They're not all flat. And, at least by eye, it looks like there's this dependence, right? So let's plot that up. Plotting up now the amplitude of this feature that you see scaled by the scale height versus equilibrium temperature. And so what you can see here is that indeed it looks like there's this dependence where above about 850 Kelvin, you start to see less evidence of these hazes in the atmosphere, whereas at the cooler temperatures, you start seeing these more muted signals that indicate there's probably hazes there. So that's good. So it looks like it's all holding together that photochemical hazes can be flattening all of these spectra. But I'll throw out a caveat as well, which is that you can also plot these as a function of how much hydrogen and helium you expect the planet to be made of. This is just based on its mass and its radius, so its density. And indeed, the sub-Neptunes, which we think have less of their atmospheres are made of hydrogen and helium, are down here, and these two Neptune-sized planets are up here. So there could also be kind of a transition we're seeing here in terms of the hydrogen-helium mass fraction versus the amplitude we're seeing. So we really need more objects just because the trend here is the same for both of these. So we need more objects that are sub-Neptunes and slightly warmer that can really tell the difference between these two scenarios.
Change the y-axis. Just block it out.
I just blocked it out. Yeah.
Okay.
Yeah. Sorry. Okay. So that's the state of the art for what we can do right now for sub-Neptunes using transmission spectroscopy. Now I want to talk a little bit about what we can do for Neptune-ish planets. So this is a Neptune-sized planet when we can measure the thermal emission instead of the transmission spectrum. So this is my favorite Neptune, GJ436b. This is roughly the same size as Neptune, and critically it also orbits this small star. So much like for GJ1214, that really helps us with the signal to noise we need for these observations. And it's about 800 Kelvin or so. So it's a warm Neptune-sized planet. And it was, in fact, the first transiting Neptune that was ever discovered. And so we have a legacy of observations for GJ436b that's unparalleled. We don't have this for any other transiting Neptune-sized exoplanet that we've observed. So we have, these are all from the Spitzer Space Telescope, and we have measurements from 3.6 out to 24 microns here. And so what we did here was naively look at what we would expect to see if we just took regular old Neptune with its 100 times solar metallicity atmosphere and heated it up to the temperature of GJ436b around 800 Kelvin. And this is what we would predict to see. So this is assuming kind of two different amounts of redistribution of heat you get around the planet versus the data here. And what you can see here, and what I'll zoom in on in a second, is that the heated up Neptune is really a very poor match for the actual data that we have right now for GJ436. So if we zoom in to where we have the highest precision measurements, which is 3.6 and 4.5 microns, we have high precision there because we've been able to measure those dozens more times. We get this. So you can see that indeed we're off by several sigma for both of these observations at 3.6 and 4.5 microns. So something is very different about this planet than we predicted. So why? What can be different? And I'll warn you that this dives a little bit into chemistry, which sometimes people complain about in astrophysics talks, but I do it anyway. So this is all controlled by the carbon chemistry in the atmosphere. So the 3.6 micron point is controlled by how much methane you have. Then the 4.5 micron point is controlled by a combination of carbon monoxide and carbon dioxide. So this is just showing where different species absorb in the atmosphere. So what we think we need to match the spectrum of GJ436b is something that decreases the amount of methane in the atmosphere, so these points get brighter, and increases the amount of CO and CO2, so those points get fainter. And so I'm going to show you how we think we can do that, and I'll warn you that it takes several steps along the way. Okay. So this is starting with our generic case. This is showing the pressure, so proxy for height in the atmosphere, versus how much of these different materials we have here. So you can see you expect to have a mix of methane, CO, and CO2. We think we need to have methane be reduced in abundance to something like 0.1 parts per million to be able to match the observed spectrum. And so we need some way of decreasing the amount of methane by orders of magnitude. And specifically, we need to do that in the photosphere, which is something around here. So one of the ways we can do that is actually by increasing the metallicity. It turns out we decrease the amount of methane in the atmosphere because of the equilibrium chemistry calculations. So that's one way, but you can see it doesn't get us nearly close enough. Okay, but let's continue with our 1,000 times solar composition atmosphere. It turns out that one of the ways that you can even further decrease the amount of methane is by heating up the interior of the atmosphere. So if we heat the interior of the atmosphere up to 400 Kelvin, we can match this 0.1 parts per million. And so what we think is happening that could heat up the interior, you're all looking at me like, why would you heat up the interior of your planet? It turns out that this planet has a high eccentricity. So what we think is going on is you're actually tidally heating the interior every time this planet goes around its star. So it has an eccentricity of about 0.15. So we think we're seeing direct evidence for tidal heating here in the interior of this planet. And then to get the abundances in the photosphere we need to assume that we're mixing this whole top of the atmosphere, which kind of locks in all of the abundances from the deep atmosphere here. And this happens all the time in planets, so this is not the surprising step.
What does that mean? What is a fast time scale?
Yeah, so the idea is that you have mixing that's happening in the atmosphere that happens faster than your chemical timescales. So you end up quenching the chemistry in the deep atmosphere.
Like years?
Oh, I think about it in terms of the eddy diffusion coefficient. So I could back it out for you based on the scale height, but I can't do it in my head up here.
Is it, I guess it's like, is it like an orbital time?
It's,
Or many.
it should be, you should be vertically mixing faster than the orbital time.
Okay, so it's fast.
Yeah,
Really?
yeah. Okay, and then this is our best fit model. So this is interesting. So the green is our best fit model where we self-consistently took into account all of this physics that was happening. So the models I was just showing you of these compositions are the green line here. So you can see that we do get closer than our canonical Neptune-like model, but we're still not matching perfectly. The pink line here, you can see matches a lot better, but this allows all of the parameters that are going into our atmosphere calculation to all vary simultaneously at the same time, and this ends up being a super high metallicity atmosphere that doesn't match the mass and the radius of this planet. And so this is interesting, because this tells us that we might be getting towards the story of what's actually going on in GJ436, and there are tantalizing pieces of evidence that it's really interesting, but the fit isn't perfect. So it's telling us that there's something we're not understanding about this planetary astrophysics. And so for a while, I was willing to chalk this up to, okay, well, GJ436b, it's the first one we found. Maybe it's just weird. Maybe when we look at the rest of the Neptunes, they'll look more like the heated up Neptune that we imagined. But then we're getting new observations. So this is for another Neptune-sized planet, and it looks incredibly similar. So it has the same really high 3.6 micron flux and low 4.5 micron flux. This is in review, so don't tweet this. So that's really interesting. So it's all coming together to tell us that there's something sort of fundamental that we don't understand about hot Neptunes. So what's next? How do we go about really understanding what's happening in these really tantalizing exoplanets that have so far proven kind of hard to explain the observations of? And so, like in many fields, this is one of the answers for what's next for transiting exoplanets. So James Webb is going to be incredible, and I will say totally transform this field. And so one of the things it'll do is we'll be able to go from having those spectra I showed you before for hot Jupiter-like atmospheres where we have, 7 points across our spectrum, to having spectra that look like this for any hot Jupiter, basically, that we decide to look at. So this is showing what the transmission spectrum looks like and what the emission spectrum will look like. We'll be able to see all these features, see different molecules, be able to see not just the water feature here in our Hubble data from 1.1 to 1.7 microns, but all these other features which are from carbon-bearing species. It's going to be amazing. And we'll also, for hot Jupiters, where we have these high signal-to-noise observations, start to be able to do really cool things. So I'll just show, I'm just throwing this out as an example because I think it's amazing. For eclipse measurements of hot Jupiters, we'll actually be able to see the subtle differences that you can see here between the different lines that represent these different, like where your hot parts and cold parts of your hot Jupiter actually are. So we'll be able to, at high precision, see these differences and be able to actually make temperature maps of our hot Jupiters from a single eclipse observation. So that'll be amazing. Okay, but now I want to talk more about the science cases we were looking at in terms of these sub-Neptunes and Neptune-sized planets, these medium-sized objects, and what I think James Webb will be able to do for them. So let's start with our hazy planets. So it turns out in any of these hazy planets I've ever run that can get this exquisitely flat transmission spectrum, we form a thermal inversion at the top of the atmosphere. So this is much like ozone on Earth absorbs in UV light. It heats up the upper atmosphere, and we end up with a stratospheric temperature inversion. Basically, the same thing is happening here, but we have these dark soot particles that are absorbing at optical wavelengths high up in the atmosphere. And so this actually has a really fundamental effect on the spectra that we see. So now we're looking at what the thermal emission from a GJ1214b like planet would look like. This is showing it in the absence of haze. And then I'm going to add a thicker and thicker haze on top of this and show you how the spectrum changes. So focus on this methane feature here and this CO2 feature here. So as you add a thin haze, you start kind of masking the spectral features that you see. But as you add a thicker and thicker haze, something really interesting happens, which is that at this point you formed this temperature inversion up at the top of the atmosphere with these haze particles, and now instead of seeing these features in absorption, you're seeing them in emission instead. So instead of having cold gas on top of hot gas, you have hot gas on top of cold gas, and you get emission features. And so we think we'll be able to observe this with James Webb, and in fact, we had most of a Cycle 1 proposal written to do this, and then, of course, the telescope got delayed. But this is what we think the spectrum will look like. This uses, I think this one uses 4 or 5 eclipses to be able to make this measurement. But you can see at high signal to noise, we'll be able to distinguish the clear case, which is the gray line here, from the hazy and then cloudy cases. So we should be able to kind of put the nail in the coffin for what's going on in these hazy, super-Earth kinds of planets by using their thermal emission spectra. And then for this Neptune-sized planet that we know its thermal emission looks super interesting and not like we predict it really should, we'll be able to go from having just photometry at these 6 wavelengths to being able to have actual spectra that look like this. This is using the green model to predict what we'll be able to do with one eclipse with near spec on James Webb. And you see that we'd be able to make a nice detection and see if we're really on the right path here or if there's something else going on in this object. And similarly, we'll be able to observe with MIRI and get the mid-infrared spectrum as well. And then the next thing that's really going to change in the next couple years with the advent of TESS is that we're going to be looking at a completely different set of exoplanets than we were looking at before. So TESS is, of course, a mission that's already flying. It's already, in fact, discovering planets. And the main advantage here is, so this is showing TESS planets versus Kepler planets that will be discovered. The Kepler planets have already been discovered. The TESS planets are simulated planets. And you can see here, if you look at the magnitude of the star they're around, there's all of these additional planets we expect to find around much brighter stars. So in just a year and a half, we'll have dozens more accessible small planets for atmospheric characterization. So we're really just going to have a different sample set to work with. Oh, and I did include, this is one of the first super-Earths that's come out of the TESS mission so far. This is in the Pi Mensae system, which is magnitude like 5.7 star, so one of the brightest stars in the sky. And we found this super-Earth in this system. So that's pretty amazing. Okay, So now in the next couple minutes, I want to talk about not how we're pushing down to do the Earth-sized planets yet, but how we're pushing across first, to look at things that are more like Jupiter in our own solar system. So this is another one of my favorite objects, WISE 0855. This is a free-floating planet mass object. It was found using WISE. It's very high proper motion. It's going across the sky at 8 arc seconds per year. I'm not an observer, but people say that's fast. And it was found using a combination of its high proper motion and its really red colors, the WISE. And based on the temperature that we see, and we can measure its distance really well, it's 2 parsecs away, we think that it has a mass around 3 to 10 Jupiter masses. We don't know how old it is, so we don't know exactly what the mass is, but it's in this planet mass range. And so if you look at objects at these temperatures, we expect basically all of their flux to be coming out in the thermal infrared longer than about 3 microns. So this is showing what we think this object should look like, WISE 0855, compared to a variety of other directly imaged planets. And you can see there, they end up basically invisible in the near infrared compared to the mid infrared. So because of this, we started a campaign to try and get a spectrum of this object from Gemini North. So this is a good place to do it. Mauna Kea is one of the best sites in the world for infrared spectroscopy. And at Gemini North, it's Q observing, so we can ask for exactly the conditions we need for these observations. So Andy Skemmer led the M-band observations here, and I led the L-band observations. And so I'll show you this pretty quickly, but this is what the L-band spectrum looks like. This is unbinned, and then this is binned at the bottom, just to compare it to the M-band spectrum, which we had to bin. So this is the M-band spectrum here that Andy led in his paper. Then this is a recent paper that I wrote about the L-band spectrum. So the very first thing we wanted to do here is compare this to what Jupiter looks like in our own solar system. Because as I argued to you before, this is the most similar object to Jupiter in terms of its temperature that we've ever been able to measure a spectrum of like this. So this is what it looks like compared to Jupiter. Again, the L-band and then the M-band here. So if you look first at the L-band spectrum, you can see that indeed, if you look closely, it looks like all of these major absorption features align. So it turns out that all across the infrared here, these are all methane features in the L-band. L-band in Jupiter is actually dominated by reflected light, so you can see the shape of the spectrum is different. We're not worried about that because our object, since there's no star there, is just glowing its own thermal emission. In the M-band, we see something really interesting. So all of these features in here are water vapor features. We see those in both Jupiter and in WISE 0855. But Jupiter has this absorption feature here that's actually from a weird species. This is phosphine. It turns out that phosphine is this disequilibrium species in Jupiter's atmosphere that we, again, expected to see in WISE 0855, and we see no evidence that it's there at all. And so that's really interesting. That tells us that something different chemically is happening in Jupiter's atmosphere compared to WISE 0855. Then the second interesting thing we found is that we see that if you run cloud-free models for this planet, you see the spectrum has, the model spectrum here, which is shown in blue, has more of a slope and larger spectral features than we actually see. And so it turns out that when we include water ice clouds in the atmosphere, we're able to get a better match for the M-band spectrum. And so this is the first evidence we've ever seen for water ice clouds outside of our own solar system. Okay, I'm going to skip those. Okay, and in the last couple minutes of my talk, I want to talk about this last step, how we might be trying to go from looking at these easier targets to trying to detect the atmospheres of something that more closely resembles the Earth. And really the question here is not like what can we actually see, like detailed characterization of Earths, but first, can we actually detect whether there are atmospheres on these terrestrial planets? So this is what I think we can really do in the coming years. So of course, if you look at the planets, the terrestrial planets in our own solar system, they have this really diverse array of atmospheres, right? That in Venus, we have a 100-bar CO2 atmosphere. It has this really hot surface, no oceans. Earth, of course, has the lovely nitrogen-oxygen atmosphere that we breathe, and it has liquid water on the surface. This is Titan. Titan also has a 1-bar nitrogen atmosphere, but has like methane lakes on its surface instead, in a methane hydrological system. And then Mars, which has this tenuous CO2 atmosphere, but a ton of evidence that there was former liquid water on the surface of Mars. And as I argued to you in the very first minutes of this talk, for the first time, we've found temperate, rocky exoplanets that are potentially accessible with upcoming telescopes. This is systems like the TRAPPIST-1 system here, which I talked about at first, B through H, with E and F being the maybe habitable ones in the middle. And then there's some other targets too. So GJ1132b and LHS1140b and 1140c, which was just announced this year. These were both found by the MERTH survey, which operates out of the CFA. And so critically, these now 10 planets all orbit very small, very nearby late-type stars. And of course, those kinds of stars are very different from something like the sun. And so we expect that these planets will have had very different histories. And so the key question that, as a field of transiting exoplanets, we really need to answer is whether terrestrial planets around these M-dwarfs can actually retain their atmospheres for billions of years. So M-dwarfs, of course, have a long pre-main sequence phase where they're very active. They're flaring stars. They have a lot of X-ray activity relative to their bolometric luminosity. They have a lot of UV activity, and they have really strong stellar winds. So all of those, modelers say, could be just like blowing the atmospheres off of any terrestrial planets in one of these systems. But we might be able to outgas additional atmospheric material and still have atmospheres. We just don't know the answer to this from first principles. And so we have to test this empirically to see if they're actually there. This is, of course, critical for the pathway of exoplanet science. We're making a choice right now between doing something like a LUVOIR or HABEX mission where we can direct image Earths around G-dwarfs, or something like the Origin Space Telescope, which would focus on transit and eclipse detection of Earths around M-dwarfs. But if it turns out that none of them have atmospheres, that wouldn't be a very compelling science case for the Origin Space Telescope to try and look at their habitability if they don't have any atmospheres at all. So this is the temperatures and the size of each of these planets that I'm going to show you whether we can observe them or not. So GJ1132b is the hottest of these. TRAPPIST-1 is also pretty hot, and LHS1140. Then the temperate objects are kind of in the middle here. And then the cold, icier planets are down here. And so this is nice. If we want to test, do planets have atmospheres as a function of, say, temperature of the planet and size of the planet, then we have a good sample here that ranges from hot to cold, and it ranges from smaller than the Earth to larger than the Earth. And so what we did in this study is because we don't know a priori what these atmospheres are going to be made of, we based it on the solar system, where we have actual terrestrial planets that exist. So we used Earth-based compositions, Venus-based compositions, and then Titan-based compositions to give us kind of the broad spectrum of different kinds of spectral features you might be able to detect for given objects. This is for one of the hot ones, GJ1132b. So that's what the transmission spectra would look like. If you look at the scale here, you see these are pretty small signals, right? These are kind of 20 to 40 parts per million signals. And then this is what the emission spectra would look like. So you can see, as you would expect, the hotter planets in our sample, things like GJ1132, are much, much brighter than the cold, icy things in the middle. So then we simulated what we can actually do with James Webb based on the simulation tools that are available. So I'm going to show you a table that shows these results. So these are how many transits or eclipses here, transits here, would be required to detect the Venus-like atmosphere, so the CO2-based atmosphere. And so I'll highlight a couple interesting things here. So a number of these planets look like they're actually good transmission spectroscopy targets. So kind of at all different planets here within a range of, I think, 4 is the best, 15 is the worst that I've highlighted. You can see, you can make a high enough signal-to-noise detection to rule out a flat line for these planets and be able to detect an atmosphere. For thermal emission, we can really only start to probe the hottest of these terrestrial planets in thermal emission. So in these, it's GJ 1132, TRAPPIST-1b. And it wasn't included in this paper because it wasn't discovered yet, but I think LHS 1140c would also be in this list of a good emission spectroscopy target. Oh yeah, and we're writing some James Webb proposals for these too. Okay, so then what would our spectra actually look like for these? So this is what we predict the spectra will look like for some of these planets. So this is TRAPPIST-1b at the top. Using 6 transits, we expect we'd be able to make a detection something like that and be able to very clearly distinguish this from being a flat line. Then this would use 9 eclipses to detect the thermal emission of the same planet. And you can see, indeed, you'd be able to tell the difference between the Venus-like planet, the Earth-like planet, and the Titan-like planet. And so I think this would be a really critical step forward for exoplanet science if we could actually do this, detect that there's an atmosphere on this warmer planet, this TRAPPIST-1b planet. I think that would tell us that the M-dwarf habitability question does not hinge on whether these planets have atmospheres. If these hot ones have atmospheres, the habitable ones almost certainly do. So that would be a really good thing to figure out. Okay, so I will end there. I'll say that we're entering an era where we can start to characterize both exotic planets, the early found hot Jupiters, but then we're really pushing towards getting to these more familiar planets like Jupiter and like Earth in our own solar system. The workhorses for this to date have been HST and Spitzer. These have really told us that the Neptunes that we found are really diverse and somewhat hard to understand from what we can see right now. Ground-based telescopes can actually detect objects that look very much like Jupiter in our own solar system. And James Webb is really going to revolutionize the whole field and, in fact, give us our first steps to understanding the atmospheres of terrestrial planets. So I'll stop there and take any questions. Thanks very much.
So what is the best or top 2 explanations for the formation of free-floating planets?
Yeah, that's a great question. So if I had to bet on it, I would say they're a mix of 2 populations. I would guess that some of them are just the tail end of star formation. And then some of them, I think, are almost certainly ejected from systems, right? We know that as planets are forming, they're often in clusters. I think some of those must get ejected at some point. So kind of figuring out what we need to do observationally to see the difference between those, I think is really important for now that we have an ensemble of free-floating planets that we can observe to high precision. I think that would be really interesting. Of free-floating planets? So objects like what I talked about, which is cold, there's just a few of them, and we don't know the masses of all of them. Some of them could have higher masses. But then there's a bunch of warmer objects as well that we can constrain the age much better because they're in young moving groups. And so for those, they're all around 1,000 to 1,700 Kelvin. And we know of probably, I would guess, something like 20 of those at this point.
What planets in our solar system have water, ice, clouds?
So Earth has water, ice, clouds. Earth also has liquid water clouds. Yep. And then the giant planets, Jupiter and Saturn, both have, we think, a water ice cloud layer that's underneath their ammonia cloud layer. So we can look at how much water is left in the atmosphere, and we see that it's depleted. And so that's used as evidence, along with the modeling that people do, that there's a water ice cloud underneath. And yeah, Neptune and Uranus should be the same, that deep underneath their atmospheres, they have water ice clouds.
Does this work inform the difference between formation, like the underlying physics of rocky planets versus gaseous giants? Like, how does that interplay with this sort of missing gap between Neptune and Earth?
Yeah, so figuring out what this kind of ensemble of planets in that range look like would tell us a lot about how these planets actually end up forming, right? So I think one of the things that could end up being really different between how we've thought about planet formation in the solar system and now that we're finding these exoplanets is that it might not have as much to do with ice lines as we thought, right? That there was kind of this previous lore that, oh, well, you need to form something out beyond the water ice line where you have a bunch of material to accrete. That might not turn out to be the case, given that we have so many systems. It actually seems much more common to stick things together in the inner solar systems. So maybe Jupiter and Saturn actually created a much weirder than normal situation in the solar system by interacting as two gas giants and really clearing out the inner solar system.
I'm just curious about people who have the number of transits. When it's 4 and then just for 13 and 17.
Yeah.
So why such sizes that different?
Yeah, so like the differences between these, it basically has to do with the surface gravity of each of these objects. So if they were all exactly Earth-sized and had an Earth mass, we would expect it to be, we would expect a scale, so like TRAPPIST-1b would be the easiest, then they'd get progressively harder because it's the scale height that's changing. But because some of these, especially like TRAPPIST-1e, is anomalously low density, so I didn't have time to talk about this, but all of them, like they don't have the masses and the radii of rocky planets. Most of these, not all of them, but most of the TRAPPIST planets are actually slightly lower density than that. So we think that it's more like something like Europa, where it has some ices on top of it as well. Not quite that much ice, but so that's really interesting and really unexpected, and I think we're all waiting to see whether that holds up long term or whether there's some problem that we're not accounting for in like the stellar radius or something like that.
And then I'll take the last question. What are you adding to the models next now that you've done like sooty hazes and
Oh, yeah.
sooty clouds before and now sooty hazes and then?
Yeah, so next I want to, the work that I didn't talk about at all that I've done on brown dwarfs, I really want to start learning from really high resolution spectroscopy what we're getting wrong in the models in detail. So like figuring out, we know that like line lists for molecules are really hard, especially at high temperatures. So we now have the observational data set to be able to map that out and like exactly where the bands are bad and where they're good, and understand that in detail. That's the plan.
Thank you for that excellent idea. And we're headed to dinner. Anyone else want to join us? We're going to meet in the lobby at 5:45.
Great.
Yeah, I saw that. Would someone mind turning the camera off, please?